Okay, it's 12:03, 12:04 in Ottawa. And so I'm Barry Goodison. I'm the chair of the CMOS Ottawa Center. And I just want to welcome everybody to this session, wherever they are located. So it's good morning to some and good afternoon to others. Just a couple of housekeeping duties before we jump into the talk. You should have on your screen the title of the talk, and I assume that that's the one you've all signed up for. So hang in there. For there are many people that are in attendance who may not be aware of what CMOS stands for or what it is. And so the Canadian Meteorological and Oceanographic Society is the national society in Canada of individuals and organizations dedicated to advancing atmosphere and oceanic sciences and related environmental disciplines. And so it aims to promote meteorology and oceanography, and it is a major non-governmental organization, which is important. But it serves the interests of not only meteorologists and oceanographers, but also the climatologists, limnologists, hydrologists, and cryospheric scientists. And as you note today, we have a cryospheric talk. A housekeeping duty, just to mention while there's most people are on board, is that the next talk, it's just been finalized, will actually be a joint presentation of the Toronto and Ottawa CMOS centers, and it's going to be by David Phillips on weather and climate, not what your grandparents knew. Dave is the senior climatologist at Environment and Climate Change Canada. In fact, this was to be a public talk at our CMOS Congress in May, which had to be canceled and went virtual, but the talk was not given. So that's going to be on November 17th at 7 p.m. and you'll get further notice of that. I want a couple of practical aspects. One, if you haven't already, please turn off your microphone, and even turning off the video is recommended for bandwidth. This will minimize any interference with the talk. And we will be using the chat function, which most may be familiar with it, down at the bottom of your screen for the question and answer. So feel free to type in a question during the talk. It'll be there, and Helen Joseph will be leading the question and answer period, and she will use that the questions on the chat to put them to the speaker. We did this the last time, and it worked quite effectively. So without further ado, I would like to turn it over to Dr. Len Barry to introduce our speaker today. Len?
Thank you very much, Barry. It's my great pleasure to introduce the CMOS Ottawa guest speaker for October, Dr. Jean Holloway. As you can see from this lower left screen, she's a postdoctoral fellow in Environment, Society and Policy Group at the University of Ottawa. She's also chair of the Canadian National Committee for the Association of Polar Early Career Scientists, APEX. And she'll say a few words about that, I think. Before we proceed, just a little background. Jean has a distinguished academic background, a BSc in Honors Environmental Geology and an MSc in Geography, both from Queen's University in our region. PhD in Geography from the University of Ottawa here. And in that PhD, she focused on the topic that is on the screen today that she will talk about. She's been the recipient over the years of numerous scholarships and training awards, including notably a $50,000 Garfield Western Award for Northern Research in 2016 to 2018. So early in her career, she's author of 10 peer-reviewed journal publications, of which 6 she is lead author. Her experience and interest are strongly oriented to northern boreal and Arctic science, or Earth System Science. And now she's working closely with Professor Jackie Dawson at the University of Ottawa and with the ArcticNet community. So our Ottawa Centre group here includes many members in Gatineau and Eastern Ontario, including Kingston. And we are very pleased to kick off our first autonomous Zoom meeting with a scientist from the region. So without further ado, I'd invite you to join me in welcoming Jean Holloway, speaking on impacts of forest fires on permafrost in the north. Thank you.
Thank you. Hi, everyone. I just wanted to first off say thank you to CMOS for inviting me to give this talk on my research on how fire is affecting permafrost in northwestern Canada. And as Dr. Barry mentioned, this presentation is based on the work that I did for my PhD at the University of Ottawa, which I just finished less than a month ago with the help of my now former supervisor, Tony Levkovich. I've shifted gears, as Len mentioned, to a postdoc now focusing more on Arctic shipping and environmental policy. But this presentation is going to be an overview of the findings from my thesis. Let me see here. I know there's a pretty diverse audience today, which is great. And yeah, there's some people, at least from my community, from all over the world. And it's such an amazing opportunity that Zoom gives us to connect and share with each other, which is something a positive thing that I'm trying to sort of bring out of the global situation we find ourselves in. Some of you are probably not familiar with permafrost, so I'm going to start off with a basic overview before diving into some of my more technical findings. And there, as Barry mentioned, there's going to be lots of time for questions and discussion after the presentation, so sit back and relax. First off, what even is permafrost? You may be able to guess just based on the name, but it is ground that remains at or below zero for 2 or more consecutive years. Permanently frozen, so permafrost. It's found in high latitude and altitudinal regions where the mean annual air temperature is cold enough so that the soil freezes in the winter, but then doesn't thaw completely in the summer. And these permafrost bodies that grow and grow as they don't thaw completely, they vary in thickness from hundreds of meters thick in interior continents, like in Siberia, for example. And then they can also be less than 5 meters thick when they're at their sort of most southern warm margin. And permafrost is, like I said, ground material that's frozen, but that doesn't necessarily mean it contains ice. So this core here, can you guys see my mouse moving? Hopefully. If not, let me know. This core here is one that I took in 2016. And you can see these lenses of ice within the core that push apart, they grow and push apart the layers of sediment. And that's, we call that something, it's called excess ice. And this core here is just frozen organics, frozen peat, which has pore ice, but none of those thick lenses that you can see in the one above. So there's ice in it, pore ice, but not excess ice. And frozen bedrock is also permafrost. And there's generally very little or no ice in that. So permafrost is just frozen ground material. It doesn't need to have ice. And as you can see from this map, permafrost landscapes cover much of Canada. So it affects a lot of Canadian residents on a day-to-day basis. A lot of Canadians live on permafrost landscapes. And even for us in the South, a lot of the issues regarding permafrost affect us, even just in terms of policy. So permafrost is a Canadian issue. Yeah, so much of the landscape is underlain by permafrost, and it can be broken down into 4 zones based on the mean annual air temperature isotherms. So continuous permafrost, which is purple on this map, is just what it sounds like. It's a continuous sheet of frozen material that's underlying the landscape. And discontinuous permafrost is just that, it's discontinuous and patchy. So cold areas of the landscape in the discontinuous permafrost zone, like for example, in the shadow of a mountain or under thick vegetation, they have permafrost present, but warmer areas of the landscape, like in a bog, permafrost is absent. So it creates this sort of patchwork environment. And in the continuous zone, it's present beneath more than 90% of the landscape, everywhere except under large lakes, where the water doesn't freeze to the base of the lake and you get above zero temperatures, and so therefore permafrost isn't present. And as you move southward, the mean annual air temperature increases, it gets closer to zero, and you get less and less permafrost. And down here at the southern margin in the zone of isolated patches, permafrost only occurs under less than 10% of the land in peatlands with thick organic layers. And so this is something that we consider ecosystem protected permafrost, meaning it's protected in the landscape by intact forest vegetation and those thick organic layers that I mentioned, sometimes up over 3 meters thick. And that allows it to persist where the mean annual air temperature can be as high as +2. So that type of air temperature is actually not favorable for permafrost presence, and it wouldn't exist here if it wasn't for that ecosystem protection. And that means that after a disturbance like a fire, it can be vulnerable to degradation. Another important component of the permafrost system is the active layer. So that's the zone at the top of the permafrost. You can see here in the schematic that I've made, the zone at the top that freezes in the winter and thaws in the summer. This is a short video from the US Fish and Wildlife Service outlining this process, simplified, but it's a good video. So watch the darker color as it progresses. That's the thawed active layer. So in the winter, it's all frozen. Early summer, the snow melts and it begins to thaw, and that thawed layer gets thicker. Over the summer, it begins to refreeze in the winter as the air temperatures cool, and eventually gets back to fully refrozen. And you could see the plant roots growing in the summer as well. And so it's an extremely important layer and process, because a lot of the biological and geochemical processes that take place in permafrost landscapes happen in the active layer, like those plant roots growing, for example. So it's an important dynamic of permafrost system. Another important feature is what's called a talc. And so that's basically just an unfrozen zone that's contained within a permafrost body or a permafrost landscape. You can have a small closed talc like this one here, which is completely enclosed on all sides by frozen ground. An open talc like this one here under this small deep lake, which is enclosed at the bottom but open at the surface, or a through talc, which is like this one here, which is open at the bottom and the top. And again, like the active layer, important processes take place in these unfrozen locations. And as you may notice in this picture, all these talcs are associated with water bodies, but there's another type of talc called a superpermafrost talc, which forms due to climate change or other disturbances. And they form when the ground that thaws in the summer does not completely refreeze in the winter. So it leaves a thawed layer above the permafrost, so suprapermafrost. And these talcs grow over time until permafrost completely degrades. So this diagram shows a schematic that I've made of what happens. It's pretty simple, but it'll explain at least the process. So in winter 1, this one here, the layer completely refreezes, the active layer completely refreezes. Summer 1 comes along, and it's a warm one. So we get really deep thaw of the active layer, so deep that when winter 2 comes around, it doesn't completely refreeze. So the depth of freezing is not deep enough such that the talc can close. And then when the more thaw takes place the next summer, Again, it doesn't refreeze in winter 3, so the talc grows. And this takes place until the permafrost body disappears at the end of, let's say winter 7. It'd probably take longer than that, but they wouldn't fit on the slide, so I just made it 7. You may notice too that since the climate's warming, theoretically, the summer active layer thickness, this guy here, is also increasing. And the depth of, this guy here. And then the depth of refreeze, which is this lighter color, is decreasing because the winters are warming as well. And that amplifies the talc development. And the last term that I want to define is thermokarst, which is basically just the irregular surface that forms when permafrost degrades. So it can be small hollows that develop, like in this picture I took here after a fire. You can kind of see these sort of pits and hummocks and hollows. Or it can be these massive features called thaw slumps, like in this image down here. Thermokarst development can be extremely rapid, and it's often much more rapid than other types of permafrost degradation from the surface down, which sort of happen at a sort of centimeter per year scale. And this type of thermokarst, these thaw slumps, can have dramatic impacts on the landscape. Most permafrost formed under past cooler climates and currently exists in disequilibrium with the current climate. And this is further exacerbated by the global climate change that's taking place, especially because the Arctic is warming more than the rest of the world. And over the last century, average surface temperatures in the Arctic have increased by about 1 degree. And similarly, precipitation has also increased, with less falling as snow, more as rain due to warmer temperatures. And as a result, permafrost at many locations has been shown to be warming and degrading in the last several decades. And another key thing is that the largest natural surface disturbance to permafrost is wildfire. It's important to note that wildfire is a natural part of the landscape, especially the boreal landscape, and healthy forests use fire to regenerate. A lot of the tree species in the boreal are adapted for fire. They have what is called ceratinous cones, which only open, they open usually after fire, and they release seeds. You can see these little cone balls at the top of these black spruce trees here. So after the fire, the cones open and the seeds rain down to the ground, and the forest regenerates that way. However, the fire regimes are changing, and we're seeing the frequency, extent, and severity of fires increasing as the climate warms. More frequent periods of drought, more intense heat waves, there's less snow, as I mentioned before, and there's more lightning strikes, and all those things have resulted in larger fires, more severe fires in the boreal and also on the tundra. And the fire season duration is also increasing and is expected to increase further due to the longer growing season in the summer. And this predicted increased frequency and magnitude of fires in combination with the climate warming that's expected is likely going to accelerate permafrost degradation and alter how permafrost recovers following fire, which I'll go into a little bit now. So fire affects permafrost by altering the surface energy balance, which is the balance between the incoming and outgoing energy at the Earth's surface. So first, fire chars the surface. You can see that here, which reduces the albedo. So more solar radiation is absorbed by the surface. There's also an increase in the solar radiation that's incident on the surface due to the combustion of the canopy, which reduces shading. So again, so more solar radiation gets to the surface. And then the open canopy also results in more snow on the ground, which insulates the ground. The loss of vegetation reduces transpiration, so the latent heat is not removed. And the ground heat flux increases due to reduction in the above ground biomass and the organic layer, which change the thermal conductivity of the soil. Basically, the important thing is that more heat gets into the ground. And we're losing that ecosystem protection that I talked about before. So it's not actually the heat from the fire itself that affects the permafrost. It's the impact on the surface and how that interacts with the climate that causes the changes. And these alterations in the surface energy balance and conditions at the surface, they persist for first few years following fire, maybe about a decade. But they return to, usually in the past at least, they return to pre-fire conditions after several decades as the vegetation regrows, which is called succession. And this includes trees, shrubs, that organic layer. And I'll note that, like I mentioned, these processes are also being impacted by climate warming. So this is how it was in the past, but it's unclear how the complex interaction between fire, vegetation, and permafrost will proceed in the future. And successional pathways have been noticed to have changed, especially in Alaska. And so it's going to be important to figure this out to predict what will happen in the future. So we actually do have a good amount of information about the relationship between permafrost and fire. This is a map that shows the studies conducted in the last 10 years. And you can see that the majority of them have been conducted in Alaska, which can be problematic because the conditions in Alaska are different than in other regions, some of the regions. On the right is a conceptual model of the factors that affect the resilience or vulnerability of permafrost to things, disturbance and other things, climate change. The main input factors like geology, climate, and vegetation are different between different regions. So what happens to permafrost in Alaska maybe isn't the same as what happens in other areas of the boreal forest. And ground ice plays a particularly important role. So there are several trajectories that I've outlined that permafrost can follow after a disturbance like fire. So here we have an unburned site. It's a happy black spruce forest. It's got a thick organic layer, nice ecosystem protection. And there is, let's say, the seasonal active layer is about 50 centimeters deep, and it's overlying low ice content permafrost. Bam, the fire comes in and it causes changes to the surface energy balance, which results in the warmer ground temperatures, more ground heat flux into the ground, and an increase in the active layer thickness. But over time, vegetation succession takes place and things return to pre-fire conditions, although the active layer will still be slightly thicker due to intervening climate warming that's taken place. So that's one. The second possible trajectory is that the active layer gets so thick, it doesn't refreeze in the winter and the talc forms. You can see that here. And then after this, the permafrost can either aggrade and return to pre-fire conditions, or it will continue to thaw entirely. So that gives us three possible trajectories for low ice content permafrost. You may be wondering why this is even important, why you should care, especially as someone who lives in the South, maybe. Well, there's a few things, but the first that I'm going to look at is that after a fire, and actually after any type of permafrost thaw, it has implications that are local, like here in changes in hydrology, but it can also have implications that are global in scale. So in terms of hydrology, basically, there's more water that's able to move through the landscape easier since it's not trapped by frozen impermeable ground. Like I I've said, the fire removes that surface vegetation, which causes changes in the way snow is trapped on the landscape, and that can increase the volume and magnitude of runoff, and can result in shifts like earlier spring freshet and increased peak flow. It increases active layer thickness, so this thawed layer is a lot thicker, and that changes how water is stored, more water storage. And then metallic development can increase pathways that water moves between the surface and groundwater, and it can flow year round because there's this unfrozen ground year round. And groundwater can then move and carry heat from burned to unburned regions, so that amplifies the effect of the fire. Although I will say that there's a lot more information needed about post-fire permafrost hydrology. So it's a key area that we need to know more about. Fire disturbance also affects the biogeochemistry and soil microbial communities on permafrost landscapes. So direct impacts include reduced nutrient uptake by that vegetation because it's now dead. And it chemically and physically alters the surface organic layer. It also indirectly, it increases rates of microbial activity because it often increases soil temperature and moisture. And it can release solutes that were previously trapped in the frozen ground. In particular, fire has long-term and potentially global consequences because it affects the ecosystem carbon balance, as increased soil temperatures and active layer thickness make previously frozen and trapped organic matter available for decomposition by those soil microbes that are really active. And that releases carbon in gaseous form into the atmosphere. And this creates a positive feedback loop where climate change causes more fires, which thaw permafrost, increase that active layer, that releases the carbon and carbon dioxide and methane, which causes more climate warming, and around the loop we go. And in fact, intense burning of peatlands and permafrost thaw may turn these sort of peatland landscapes into carbon sources rather than carbon sinks. And that has potentially global consequences. At sites with higher ice content, along with those processes taking place at low ice content sites, which we just discussed, like the active layer thickening and talc formation, there are additional impacts due to melting ground ice and subsidence. So after a fire, you can get thermokarst and pond development, the expansion of unfrozen bogs and the thaw of peat plateaus, and on hill slopes, you can get things called active layer detachments, which I have an example of here. This is from a fire that occurred in the Yukon. And basically what happens is the ice-rich layer right at the bottom of the active layer melts, and all the water, it makes the ground unstable. And the thawed active layer detaches from the permafrost, and that soil moves downslope in a type of landslide. You can see the sediment here rushing down slope into this stream, and that can have implications on the landscape. Another major implication of ice-rich permafrost thaw is ground subsidence. So ice within the soil melts and the empty voids collapse. The ground sinks. Watch the soil on the left actually go. It thaws and sinks very quickly. The core on the right has very little ice, this one here, and it remains actually pretty intact after it thaws completely. And the core in the middle is basically pure ice, and it appears to thaw and collapse slower because of the latent heat that's required to melt pure ice. Imagine if there's a road or a house built on the core on the left. Imagine what would happen when it just sinks and disappears. So yeah, ground subsidence can be very destructive to infrastructure. There are major problems with roads built on ice-rich permafrost actually, and this is a depression that caused by permafrost thaw along the Alaska Highway. And I've actually hit one of these bumps going about 80 in my truck. And let me tell you, you go flying. It can be destructive. And this is the famous crooked building from Dawson City in the Yukon. But damage like this from ground subsidence is taking place all across the Arctic. And it also has major consequences for the landscape and vegetation. So fire can cause wetland formation, like I mentioned before, when ground subsidence and water inundation occurs. In these settings, this bog here, you can see this area, it thaws into these treed peat plateaus, and the bog expands. And this affects how humans and wildlife are able to use the landscape and move about the landscape. And it also changes the hydrological and biogeochemical processes. So hopefully everyone's following along. We're about halfway there, I would say. And just to summarize, fire causes permafrost thaw. If you don't remember anything else, you can just remember that. So although we do know a lot about what happens to permafrost following fire, that I've just given you a nice background of, some significant knowledge gaps still remain. Specifically, there's a lack of long-term information and limited direct measurements of certain variables which affect post-fire permafrost dynamics, including things like snow depth, burn severity, soil moisture, and how ground ice content and subsidence and thermokarst development affect permafrost following fire. The majority of the studies on post-fire permafrost conditions are on high ice content sites and neglect low ice content sites, which are still important. And generally they have been focused on the near surface, so the top 2 meters of the permafrost. And yeah, that neglects conditions at depth where permafrost can thaw but still exist at depth. And addressing these unanswered questions is important for understanding how to predict how permafrost may react in the future with those shifting fire regimes and with climate warming. And so my work addressed these knowledge gaps, some of them, most of them, through in situ measurements and analysis of permafrost conditions following fires that took place over the last half century. And the real spark for my work, if you will, was the abnormal fire year of 2014 in the Northwest Territories, where 3.4 million hectares burned, making it the largest fire year on record in the NWT. And the fire affected the majority of NWT residents, including evacuations and health impacts caused from things like smoke inhalation. And over $56 million was spent fighting the fires. And although that's horrible, those things are horrible, the fires did allow access to sites across a huge range of environmental conditions because they were so large. And a lot of them burned across the highways. So that allowed me to take advantage of that when building my study framework. This is a map of my study area, including over 80 burned and unburned sites. This work took place on the traditional land of the Yellowknives Dene, the North Slave Métis, the Tlicho, Decho, Catlo Diche, and Dene Ta First Nations, whom I'd like to specifically thank for allowing me access to their land. So Masicho. And my study sites extend across about a 650 kilometer latitudinal transect, spanning through the discontinuous zones of permafrost. So you can see here from the isolated patches, there's some sites there, all the way to the extensive discontinuous permafrost up near Yellowknife. And this includes sites across a wide range of environmental conditions, including 2 ecozones. And you can note from this map that the region is comprised mostly of low ice content permafrost, which is lighter blue on the map. There are local areas of higher volumes of ice that don't show up on this scale, but for the most part, it's low ice content. The climate in the region is subarctic and continental, with mean annual air temperature of about -3. Although the figure on the right here shows that the region has undergone approximately 2 degrees of warming over the last 50 years. So my studies made up of 2 main transects. The first is a series of sites that I set up following that record fire year in 2014, with an additional site set up after a fire in 2015. And I used these sites to monitor the changes in the first 5 years following the disturbance, specifically to identify what variables determined the scale of the impacts on the permafrost. And then the second transect is a resurvey of sites which were originally investigated by Roger Brown in the 1960s. And this allowed me to get a long-term perspective on how permafrost has changed over the last 50 years due to the regional climate warming and fire in a lot of locations. So I used several methods to establish how the permafrost was changing, including air, surface, and ground temperature monitoring at stations, which you can see in this picture. Where I could, I water jet drilled into the permafrost to install thermistors at depth, or else I just installed them within the active layer. And I also measured snow depth using eye-button temperature loggers mounted on stakes, like you can see there. At all sites, I determined the depth of the frost table by probing the ground with a 1.2 meter titanium rod. When you meet resistance, you know you've hit the frost table. This was done repeatedly for certain sites annually to establish how the active layer of the frost table was changing over time. I dug pits, a lot of pits, and where possible, I took frozen ground cores and measured the ice content, the soil moisture, grain size, organic content, and bulk density of the soil. I also established the burn severity of the 2014 and 15 fires by measuring the residual organic layer thickness. So you dig a pit and you measure how much of the organic layer is left remaining after the fire, and also the depth of burn. So black spruce trees shoot out these little adventitious roots, you can see in this picture, which remain after the organic layer is consumed by the fire. And measuring the depth of these roots allows us to establish the depth of the burn. So how much of the organic layer was there before and how much is there now, find the depth of the burn. And understanding and monitoring discontinuous permafrost like I did can be difficult because you have those complex interactions between topography, the vegetation, the hydrology, and the surface and subsurface characteristics that are extremely heterogeneous across the landscape, and the permafrost is patchy. So it occurs in some areas of the landscape, but not others. And often there's not a surface expression indicating where the permafrost is present and where it's not. And that's particular for where permafrost occurs in forested sites or isn't ice rich. So you don't get that thermokarst developing that you can see from satellite imagery. And furthermore, where permafrost is degrading, we need to monitor it using techniques that extend below the near surface, like I talked about, to fully understand the timing and rate of thaw and what's happening at depth. So to do this, I used a geophysical technique called electrical resistivity tomography, or ERT is how I'll refer to it now. The thermometer is this orange box here, which is really heavy, and I had to haul through the forest, like sometimes up to 1 kilometer. And it shoots current through 2 metal rods, which we insert into the ground, called electrodes. And it measures the voltage. So it shoots the current and measures the voltage of 2 inner electrodes. And the basic principle of ERT is that the electrical resistance of water in the ground is very low, and ice is several orders of magnitude higher. So that allows us to interpret areas that are likely to be frozen. The majority of my ERT surveys were 160 meters long, and that allows me to see to up to 25 meters depth. So instead of seeing the top 2 meters, now we're seeing to 25 meters. So you can get a better picture of what's going on. I measured ground subsidence by conducting repeat surveys using, you can see here, the zip level altimeter. And I measured the relative elevation change in burned areas compared to areas which remained unburned and unchanged, like if there was a bedrock outcrop that wouldn't subside. So that gave me an idea of the relative ground subsidence occurring across the transects. So my findings show that over the past 55 years, permafrost has persisted, which is shown in blue here on this figure, even though the climate has warmed and after fire as well. However, it did degrade at a number of sites, at 36% of the sites, which is shown in red, including sites at the southern end of the transect down here, where the climate has warmed so much that it's no longer suitable for permafrost presence, even under thick organic layers. So there's no ecosystem protection there anymore. This is an example of an undisturbed site where permafrost has persisted. So this is the ERT profile here, the 25 meters depth. And you can see the cold blue colors in the figure are high resistivities, and they extend to about 5 meters depth there, which I've interpreted to be frozen ground. And then this is supported here by this frost table depth, which is about 60 centimeters in the late summer. So I've interpreted that site to have about 5 meters of permafrost, and it's persisting despite quite warm mean annual air temperatures. In general, sites where permafrost persisted had thicker organic layers and fine-grained soil. And on the left here, you can see the percent of sites with organic layers thicker than the value shown here. And about 90% of sites where permafrost persisted had an organic layer thicker than 40 centimeters. So that seems to be sort of this threshold. Whereas only about 20% of sites where permafrost degraded had organic layers that thick. Permafrost persisted at 80% of sites with fine-grained substrates, but degraded at the majority of sites with coarse-grained substrates. So yeah, permafrost likes thick organic layers and fine-grained soil. In terms of frost table depths, surprisingly, there wasn't that much difference between 1962, which is here, and 2017-18. And this is the one-to-one line here. And a lot of the sites fell within, very close to the one-to-one line. The mean frost table depth in 1962 was 64 centimeters, while for the same sites in 2017-18, the median was 66. Although it's interesting to note that a lot of the sites that had greater frost table depths were recently burned. So these are photos from 2012. And you can see that so the burn happened the photos are taken in 2017, the burn happened in 2012. So despite there being 5 years in between, there's still, you can see the ground char, the trees haven't recovered. So clearly here, the active layer is thicker due to that burn. Similarly, if we zoom to the more recent past, after the 2014 fires, I found similar results linking frost table depths to burn severity. So this is the unpopulated graph, and before I populate it, I'm just going to explain what you'll see. On the y-axis is the first quartile of the frost table depths, and on the x-axis is the portion of the organic layer lost, so the burn severity. Each year is shown by a different symbol, and each site by a different color, and the unburned sites are green. And what I expected was that the frost table depths would increase with burn severity. And indeed, that's what I saw. So you can see the change happening over time here with this pink site, for example. So 2015 is the circle, and it increases to 2019, frost table depth increases. The arrows indicate where the frost table was greater than the length of our probe. And you can see that the frost tables are generally shallower and change less over time at those unburned sites. And we find similar results for other soil characteristics, including higher frost table depths at sites with low gravimetric moisture content. So here, for example, and coarser textured soil, which is here. I also saw decreases in the resistivity at sites between years, at all sites, including unburned ones. So decreases in resistivity indicate that there's more unfrozen moisture in the soil, which is an indication that permafrost is thawing or warming. And we can see that the average resistivity is decreasing more at burned sites with thin organic layers, which are shown in orange on this figure. And those sites also have lower resistivity values overall, generally. These are some time-lapse ERT tomograms for a burned and unburned site. So a time-lapse shows the difference between the resistivity in 2015 and 2018. Green indicates areas where little or no change is happening. So that's 0 here, this kind of green colors, and the cold colors are increases and the warm colors are decreases. You can see that a lot more change is happening in the near surface at the burned site, like that, compared to at the unburned site, which are mostly kind of green in the sort of 0 range, including these purple areas here, which are up to 70% reductions in resistivity. This is an example of one burned site in the middle of the transect on the Taiga Plains. These are the conditions in September of 2015, 1 year following the fire. And I did some lab work that indicated a resistivity threshold of about 80 ohm meters at this site between frozen and unfrozen soil. So you can see here, I've outlined what I determined to be frozen ground. And that's about 5 to 10 meters of permafrost, this high resistivity body, the blue colors. And there's also a 60 centimeter frost table sort of in this middle portion here, but the frost table depth is really deep on the other side of the transect. And in 2018, 4 years after the fire, there's no longer any frost table detectable across the site by our 120 centimeter probe. And the resistivity had dropped substantially across the entire profile. That 80 ohm meter threshold that I've outlined, it's a lot deeper, and actually this sort of portion here has degraded entirely. And I'll flip back and forth just so you can see the changes in more detail. So big changes is in only a few years. And I also installed a borehole at this site in 2015 into the permafrost that was there at the time. And you can see that the temperature in 2016, which is shown by this dashed line here, has warmed significantly by 2019. So big increases in the temperature profile. Although the deep sensor did fail, so it's supposed to extend down farther, it failed in 2019. I did extract a positive temperature measurement on December 1st of 2018. So that positive measurement means that it's no longer permanently frozen because it has thawed for some portion of the year. So that validates our ERT interpretation that the permafrost had degraded in that area. And the likely cause of that degradation is post-fire ground subsidence and water inundation, which occurred because there was excess ice, those big ice lenses at that site. And when the permafrost thawed, warmed, that took place. And you can actually see here in 2019, I'm basically standing in a pond, which wasn't present when I first set up the monitoring site in 2016. So I'm gonna wrap up with a few slides about some conclusions. My research shows that permafrost is degrading in this region due to both climate warming and fire, but the important thing that I want to highlight is that it is persisting in a lot of locations, mostly at sites with those thick organic layers and fine-grained soil, and sites with high moisture content. So there's sort of a notion and maybe a fear that permafrost is all thawing and it's all scary, but it is persisting in a lot of locations. So please remember that. Cold permafrost sites at the northern end of my study transect appear more resilient, even when they're severely burned. So at this site, for example, my most northern site, there was absolutely no residual organic layer, and the permafrost temperatures actually cooled over the recorded period. So there appears to be some sort of threshold there in terms of the mean annual air temperature that it doesn't really have an impact on the permafrost. The fire doesn't. And permafrost in the sporadic discontinuous zone remains resilient to fire, even remains resilient to fire if it's protected by a thick organic layer and does not experience the ground subsidence and thermokarst that I was just talking about. And that includes this site as far south as 59.3 degrees north, which is quite far south, and that was a surprising finding. Due to the general low ice content of permafrost in my study area, thermokarst development was pretty limited. A lot of other studies are finding way more dramatic rates of thermokarst expansion. And I think that's just because we're measuring different types of sites, different landscape conditions. But where I did see thermokarst happening, that water inundation and permafrost thaw was rapid and substantial, like that last site that I went through with you guys. So historically, over the long term, it appears that the majority of sites do return to pre-fire conditions, as I didn't see any difference in active layer thickness at sites which burned up to 40 years ago. So that vegetation succession has taken place, that active layer has regraded. The change is mainly in the near surface, and where observations were possible for permafrost at depths greater than about 5 meters, it seemed relatively unaffected in that 5-year time frame after the fire that I was monitoring. But my long-term results from the past only indicate that permafrost has been resilient under those past climate conditions. And my 5-year recent short-term observations, from that I can't conclude whether permafrost will recover to pre-fire conditions in the future with a warming climate. So those are unanswered questions, although there's some modeling studies, some underway by me and colleagues, and also some from previous literature that show that it is likely that as the climate continues to warm and fire becomes more frequent and severe, the permafrost in the discontinuous zone will become more vulnerable to fire. So with that, I'm just going to quickly thank everyone who's helped me on this project. So Jen Balzer, Merritt Turetsky, Michelle Mack, Jill Johnstone, and Steve Cumming were the PIs, in addition to Tony, my supervisor, on this project, and wouldn't have been possible without them. Some colleagues and co-authors and people who have helped me in the lab, and everyone who helped me in the field as well. I know some of you are online today, and carrying all that heavy ERT equipment through the burned forest, I would not have been able to do it without you. And as Len mentioned, I'm going to take a few minutes just to talk about, to put on my other hat and tell you a little bit about the Association of Polar Early Career Scientists. I'm the chair of the Canadian National Committee, and we just elected our new board for the 2021 term, but we have hundreds of members all across Canada. So APEX provides a network for early career researchers, ECRs, is what we call them, and helps facilitate communication between ECRs with each other. But we also advocate for ECRs at the national scale. And we create lots of things like career development opportunities, as well as conducting education and outreach activities for scientists, but also for the general public. And we're always doing lots of different activities. I've gotten a lot out of, for my personal career, out of working with Apex. So if you're an ACR and you're interested in becoming a member or joining me and the other members of the board, feel free to contact me or check out our website right here. Yeah, so with that, let's begin the question and discussion period. And if your question doesn't get answered today, or you'd love to chat or collaborate, feel free to contact me. This is my email address there.
Great. So it's Helen Joseph here. Thank you very much. You can hear me, Jean?
Yep, I sure can.
Okay, everyone else can too, I'm sure. Thanks very much for an awesome presentation, very educational. So you've really enlightened us a lot. And we've got the questions popping in the chat room here quite quickly. So I'll field the questions and pose them to you. So here we go. So the first question is from Art Hunter, and he's asking, were there any associated studies that consider the impact on the life cycles of bugs, birds, rodents, fish, mammals, but I guess it's sort of ecosystem impacts in the post-burn areas and the growth of the talix?
That's a really good question. I haven't seen any. That doesn't mean that there isn't any. I mean, I would say that that talic development and active layer thickening would actually possibly be beneficial for certain, especially burrowing animals, rodents, and bugs, because yeah, the frozen ground isn't really a hospitable environment to live in. I know in the high Arctic, there's lots of studies being done on like fox dens and how the permafrost thaw is changing that. That's not related to fire, but it is related to sort of, yeah, that active layer thickening. So I'm sure there is a lot of work being done on that. I know a lot of my colleagues work on how changing fire regimes are affecting lichen growth, and that's I think what caribou mostly eat. And so changes in how that lichen is growing really affect caribou diet, and I think the changing fires also affect their migration patterns. So there is lots of work being done on that kind of thing, not related to what I do, but yeah.
Thanks for that, Jean. Next question is saying, great presentation, thank you. And the question is, what is the process involved in getting permission from the First Nation communities in the considered study area?
That's a good question. I actually was really lucky because I did all of that permit work for this project, which at the time I maybe resented my supervisor a little bit, but it did give me a lot of really good experience. So each territory has a body that you apply for a research permit. And so in the Northwest Territories, it's the Aurora Research Institute that's up in Inuvik, and they liaise with the communities and the researchers. So each community in the each area, First Nation that I work in, had to look at my proposal. We had to do sort of a plain language summary, and then also provide some what our expected sort of impacts would be. So for example, for me, I had to leave those electrodes in the ground. So things like that, I had to report that to the communities, and each of the communities signed off on before we were able to go conduct any of the field work. So each year you have to renew your research license, and then provide a summary and an update to the community after you conduct each year's research with sort of what your findings were and things like that.
I'm sure it's an onerous process, but I think the advantage of it is that you really get to know and work with the communities a little bit more, so they understand what you're doing and get their feedback. So
yeah, and I actually I find it really important to actually go into the communities and speak with them. So I did present a lot of my results especially in Fort Providence, where I worked out of a lot. And I was able to speak with their chief about what his concerns about permafrost were. And I went into Kakisa as well, which is sort of about 3 hours south of Yellowknife. And they told me that they'd seen landscapes burn that they'd never seen burn before in that 2014 fire. So it was very severe, and those types of observations are invaluable. And I do really hope to work more with communities in the future, especially in my new position, my postdoc position.
Great. So Barry Goodison's got the next question up here for you, Jean. He says, the ability to compare with Roger Brown's work in the 1960s is very interesting. Are there other transects which could be compared to look at long-term change in permafrost conditions, or new transects being established for comparison in the future?
Yeah, so Roger Brown did amazing work, and he basically, so that transect that I showed you, he did that all over the north. There's my supervisor and one of his previous grad students worked on basically a parallel study to mine along the Alaska Highway in the Yukon, and they found very similar results. So there's that is basically the only transect of that kind from the past that I know of. It's really hard to find information on permafrost prior to the 1980s, actually. Not to toot my own horn, but yes, I think that that study in particular will be really, really useful for sort of long-term observations on how permafrost is changing. In terms of new transects, I know that that's one of the main, I think a lot of work is being done right now to sort of figure out what measurements are being taken and where, to try and consolidate all the information we have. Because I think in the past, scientists haven't done a very good job at communicating with each other. And I think we have a ton of data, especially on permafrost, even in just the NWT. So I know the territorial government, for example, is doing a lot to make a database for where there are monitoring sites, who's monitoring them, what equipment there are. And I've contributed a lot of my site information to that database. So I know there is some work being done to try and establish these types of data sets for the future. Another good one is, I'm trying to remember what it's called now, but there's a couple through the International Permafrost Association. One's called CALM, Circumpolar Active Layer Monitoring. And it's basically so that everyone does the same, takes the same type of measurements using the same technique. And that allows us to compare these sort of active layer changes across the Pan-Arctic. And the International Permafrost Association has that maps of those up on the website. I think they also have a similar project for ground temperatures. I think it's called, I forget what the acronym is, but yeah, the IPA website has a lot of really good information about that stuff if people are interested.
I think your comment, Jean, about their, I think there is a sense of more collaboration amongst researchers Pan-Arctic now. And you see that in terms of the increasing amount of networking and whatnot. So that all builds well there.
Yeah.
You have a great shout out from maybe someone you know, Geneviève Descré-Timmons. Says, great presentation.
Geneviève helped me in the field for a couple of years, so thank you, Geneviève.
That's great to see. Michael Steves is asking you, could permafrost melt release bacteria or viruses?
So Christy Duncan, I forget what her actual title is, our chief science officer, she did her PhD looking at that actually exact thing. So I think her work was done on Svalbard, but it's just the same process that I was talking about. So that active layer thaw, that these old relict viruses that were trapped and immobilized in the frozen ground are then sort of released into the environment. So I believe she was looking at Spanish influenza, I think. I haven't read that paper in a really long time, but yes, so the short answer is yes. So that's another sort of strange global impact of permafrost thaw.
Imagine, eh?
Yeah, very weird.
Yeah, I know. It's so another question here, John Pierce, another great presentation. Do you have plans to go back and repeat some sampling to establish trends? And I don't know if that's going to be possible with the way your postdoc is taking you, but
yeah, I'm shifting gears because I got a really awesome opportunity, and I'm really excited to work with Jackie and kind of go in a new direction. But that being said, I do really think that I will go back into the permafrost world eventually, maybe after my postdoc, for an academic position or a government position. I think if I don't, I've set up with some of those principal investigators who I shouted out in my acknowledgement slide. They've sort of taken over monitoring and upkeeping those monitoring sites that I set up, because I think the intent of my project was to be able to monitor the conditions for a long time, not just the 5 years of my thesis, but to show those long-term trends. I mean, I would really like to go back 10 years post-fire, because that seems to be when that vegetation succession takes place. And if things are really shifting, that would be when we would see it. It's hard to know right now what's going to happen in the future. And I do have some modeling work underway. It wasn't included in my thesis because I really wanted to get that done, and it was taking too long. So it's underway right now, and that should help us sort of figure out what's going on. But yeah, modeling is it's ideal. It's not always exact for what will happen in the environment. And I'm doing the best I can to use a lot of inputs that I've measured. But yeah, there's still some issues with it.
yeah, you don't know where your future is going to take you postdoc, so you may have opportunities yet. A question here from someone, Robert Jones, I have it. He says, in the 1970s, he flew with the Canadian Ice Service over much of the Arctic, especially in the Mackenzie Delta area. We observed what was then called pingos. I recall, he says, that they were to be areas of fine permafrost and were usually circular. Was that correct, he's asking? And is there a newer name for these? I noticed you didn't talk about pingos.
I didn't. So yeah, that's absolutely correct. And they are still called pingos. And so they're really ice rich features. And so all that excess ice, which I showed in those cores, I guess I could go back and find a picture. How do I go back here? Sorry, 1 second. So excess ice, this is a better picture. Excess ice, like in this core here. Basically the whole pingo is made up of that. And that excess ice expands and causes it to grow out of the ground. And in the delta, I think a lot of the surrounding area is marshland or even like water. And so that ice causes the pingo to raise up, and then that changes the surface conditions. So it raises, it's more exposed to wind, and so the snow blows off, and that actually cools the ground more and causes more ice to form. And so it's sort of a feedback, and it grows and grows. And so a lot of them, I would say, are thawing now. I would say in the 1970s, they probably weren't thawing as much, but they're always circular in form. And they are really beautiful. If I don't have any pictures because I've only seen one when I went to Svalbard to study. I haven't seen any in the Yellowknife region. A lot of them occur on the delta.
Mm-hmm. Okay. Thanks. Another shout out, great presentation. And the question is building on your response to Thomas LaBelle's question that was about working with the Indigenous permitting and regulatory process, but they're asking, could you speak to the role of permafrost research in building a bridge for knowledge transfer between Indigenous communities and Western science bodies?
That's a good question, Julie. Yeah, I think I think in permafrost science, we could do a better job of working with Indigenous communities and especially using traditional knowledge. I think it's coming, and I think it's coming in a lot of scientific disciplines. And I think permafrost is a really important discipline because a lot of Indigenous communities they live on the permafrost and it affects their day-to-day life. So my results could be really beneficial to them, and I have to do a good job about going back to the communities and sharing knowledge, and so transferring knowledge in that direction. But I also have to listen and sort of have a two-way transfer of what their knowledge is, what their needs are, and also sharing my results with them in a way that's accessible and relevant to them. Sometimes a lot of the questions that I think are important or that I care about might not actually be important to the communities, and they have different research needs and interests than I think what like sort of base Western science sort of deems important. So yeah, I think it's a two-way transfer of knowledge, and I don't know what the role of permafrost research specifically may be. I just think, yeah, it is an important part of sort of the day-to-day lifestyle and living conditions for the communities. So I actually find it can be kind of hard to explain what permafrost is and why these things happen, even to some of my my family members, because it's hard to see. You can't see it. It's sort of intangible, and sometimes it's hard to explain some of the processes that are happening. So I think in general, it's really important for scientists to practice science communication and learn how to effectively share our results in a way that like people can understand. Hopefully I've done that okay today, but I never know.
I thought that's a good lead into, yeah. No, I think you've done a great job today. I think maybe I've covered off the questions that have come up in the chat room. I appreciate, Jean, that you've put your email address on your last slide there, so that if there are questions that you would obviously welcome somebody just giving you a shout as to something to follow up on. So in closing then, I would like to, on behalf of all of CMOS, thank you very much for joining us today and giving what I'd said was a very educational a presentation and discussion. And you've obviously done some excellent research, and we certainly wish you well with your postdoc. We have had Jackie come in and speak actually at CMOS luncheon, so we know you're in good hands and working with Jackie and her team at Ottawa U, and maybe we'll see more of you and or Jackie's team in the future.
Awesome. Thank you.
Yeah, and I would like to invite all the participants today to continue to follow the CMOS website. You'll see the updates there and details on the upcoming talks, the Jay Phillips ones that Barry mentioned at the beginning. So continue to follow on that. And thank you again, Jean, and thank you again, everyone, for joining us today. It's a good way to stay in touch, even though it's virtually, but stay in touch and know that everyone's doing fine. So please, everyone, take care and stay safe. Thank you.
Everybody, thank you for coming.
Okay. Bye.